afternoon. My name is Tom Austin. I'm a professor at San Jose State University and also one of the co-founders of 0Chain. And today I'm here to talk about the work that we have been doing on our storage protocol. I want to talk a little bit about 0Chain's ecosystem first and what it is that we're trying to do. Our tagline is fast, flexible, free. And we're trying to be a fast, flexible, free dApp framework for developers. So let's take a look at the first aspect of that. Fast. What we mean by that is we offer very quick transaction time with quick finalization on our blockchain. To provide this, we need to make sure that any of the other work we're doing doesn't slow down our mining network too much. The flexible portion is that we're trying to make our system as modular as possible. And in particular with storage, we want to make sure that we introduce as little dependency on the underlying blockchain as possible. In theory, we only want it to be designed so that it can be used on any blockchain we wanted to make use of storage. And the free part, well, it's zero cost. So if you happen to own a bunch of 0Chain tokens, you can use them to get access to certain storage resources, but you don't lose your tokens. Once your contract period is done, you actually regain use of your tokens, which you can then use to renew storage, or you can sell or do whatever you want with them. So one thing to note here is that 0Chain is under active development. All the things that I say today are true as of now, but could change as of tomorrow when we update our protocol. Nonetheless, we feel that our storage protocol is reasonably stable at this point, so that we're comfortable talking about it. So, how do we go about providing storage to dApp developers? Well, we need to consider who the different players are in our system and what their resources are, what their responsibilities are, and what their goals are, really. First off, we have Alice. Alice is our client, following the typical security convention of having Alice, Bob, Charlie, and so on. So Alice is expected to have a certain number of 0Chain tokens, and she uses them to buy storage or other resources that she needs. Now, you note that buys is in quotes. Again, she doesn't really lose these tokens, she just locks them up for some period of time. And once she has done this, she gets access to a certain right of storage, that she has a certain number of gigabytes that she can use. In addition, she's going to want to be able to read that data, update that data, and she wants to get some additional resiliency for her data, so we expect that she will use erasure codes to make sure that in case a blobber disappears from the network unexpectedly, that she can still reconstruct her data. Additionally, if she wants to keep that data private, she is expected to encrypt the data on her end. Now, the next entity in our system is Bob. Bob is a blobber, and Bob's only job is to provide storage. Now, because he has a specialized role, we expect that he does a pretty good job of it. He's able to give us fast response times in getting back that data. So this is a distinction between us and some other protocols in that we're less lenient on who we're willing to let join our network. And in exchange, though, it gives us a better quality of our network overall. Bob is also expected to have a certain number of 0Chain tokens, which he stakes in case that there's any problems with his performance. This serves as a mechanism to make sure that he's actually doing his job. In return for all of this, he gets a number of 0Chain tokens that are newly minted, and he gets paid in particular for just storing a file. And to represent bandwidth, he also gets paid for every read and write that he does. So because he gets paid for the more resources he has available for storage, it's in his interest to make his as good of a quality as machine as possible. Now, critically, Bob is not a miner. That is his separate role. Bob's only job is to provide storage. The mining network's primary job is to verify transactions. So, in their role as the storage protocol, they're also expected to assign storage to make sure that when Alice wants to store data with a blobber, that the mining network has to choose which blobbers will actually fit what Alice's requirements are. His job is also to verify that the blobbers are really storing the data that they claim they're going to store, and to ensure that the blobbers are paid for the work they're doing. Lastly, if any disputes or conflicts come up, it's the mining network's role to step in and arbitrate in those cases. Now, of course, here on this slide, I just have a single miner, but we all know that's not the way things work. We actually have a network of miners. So that single miner is actually a stand-in for our whole mining network. Now, there are several other systems out there that provide storage related to the blockchain. One of them is Filecoin. Filecoin uses cipher block chaining, and with these special variants they deliberately slow down the encryption and decryption process to introduce greater latency into their system. Now, with this mechanism, it makes them easier to catch cheaters, anybody who's not really storing the data or who's trying to really just store one copy of the file when they're expected to store multiple replicas. And the only downside of this approach is it slows down how quickly they can provide the data. Now, they try to address this with a secondary retrieval market, so you could have locally cached copies of the data. And it's very interesting work. It just didn't quite seem like a fit for the things that we wanted to do. Our approach is closer to that of SIA and storage. In these systems, a Merkle tree is used to represent the file contents that an entity is expected to store. And the data is also used as erasure codes to make sure that in case anybody disappears or is not performing up to expectations, it's possible to recreate that information. The key distinctions between these approaches and ours is that we really try to decouple the role of being a miner from the role of being a blobber. Additionally, we're zero cost. So in our protocol, although you have to lock up a certain number of tokens to acquire storage, you do get those tokens back. Okay, so we'll talk a little more about the first step that Alice would go through, which is once she has her tokens, how does she use them to acquire storage? So she buys these by locking them up with a transaction on the blockchain. Critically, this locks up her tokens for a set period of time and gives her access to storage resources for that same period of time. What this means is that even if the 0Chain token price happens to fluctuate and go up and down, Alice is shielded from all of that. Whatever agreement she made up front for that period of time, she has access to that level of storage. Once the terms are up, her tokens are unlocked, and she can do whatever she wants with them. Now, once she's acquired her tokens, she wants to use them to actually either upload a file or to be able to access some other resources on her network. So, when she wants to set up a connection, she writes a transaction to the blockchain, and the goals of this setup are to make sure that we assign the right blobbers to handle Alice's request, that we commit the blobber on what data the blobber is actually supposed to be storing, and when possible, we also want to commit Alice so that we know that Alice and Bob agree on the file contents. And lastly, we want to make sure that we set up a secure connection between Alice and Bob so that they can communicate safely. Okay, so in this picture, we have Alice. She has a file that she wants to store, so she writes a transaction to the blockchain. She specifies her ID, the client ID, that uniquely identifies her. She then specifies the data ID, which is a name she chooses to represent that particular chunk of data. And she selects a timestamp to make sure that this is a fresh transaction. She also can, when possible, specify the Merkle root so that we can use that as a form of auditing to make sure that Bob is actually storing the right thing. And there's a params field that is deliberately vague, depending on whether this is a read transaction or a write transaction or what other different requirements she has for this connection. All of this can be specified here, and we've left this deliberately vague. Now, she also includes her signature to make sure that this is all a transaction that she authorized. Now, the mining network will take this request and assign an appropriate blobber to handle her request. So now Alice knows that she is working with Bob. So in the setup we have on this diagram, we have one transaction. Conceptually, because we're using erasure codes, any operation is really going to translate into a group of transactions. But in our system, in that group, each transaction is represented as its own thing, which gives us more flexibility. So once Alice actually knows she's dealing with Bob, she sets up a secure connection using TLS. And her first message is to send this transaction ID, which is a triple of her ID, the ID of the data that she wants to store, and the timestamp. And this lets Bob check the blockchain and make sure that this is actually an authorized request by the mining network. Now, everything that's needed is set up, so Alice and Bob can communicate, read and write data back and forth, and the mining network doesn't have to be evolved. So the miners can now focus on verifying transactions. All the heavy lifting is going to happen directly between Alice and Bob. Now, I'm going to drill in a little bit more on what happens with these reads and writes. Our process centers on the notion of having these special markers. Now, markers are basically like checks that Alice is writing to Bob to pay for the work that she wants him to do. All of these are signed by her so that she can't deny it later. And the blobber will later redeem these markers when this connection is completed. So if any disputes come later, or if Bob is ever actually challenged to provide data, these markers will actually give him some proof to back up that he's doing the right thing. So we'll take a closer look at the format here. The read marker includes a constant at the beginning, just to make sure we don't mix this up with any other marker formats. We have the transaction ID, which ties this back to a particular transaction that Alice created on the blockchain. And this prevents Bob from actually trying to cache in these markers multiple times. We have a blobber ID, which is sort of like a to field on the check. And this means that if Bob and Charlie are both doing work for Alice, they can't pass these markers back and forth and both get paid for doing the same work. We include a block number, and this is the block of the Merkle tree when you get down to the leaves. So this is block in the data sense of the word and the data storage sense of the word, rather than in the blockchain sense of the word. Lastly, we have this I value here, which is a counter, which starts at 0 for each new connection and is incremented with each operation. And this means that if Alice is continuously reading from the same block of data over and over again for whatever reason, Bob is still going to get paid for each and every operation. We have write markers, which are very similar in format, with a different constant at the beginning. But the most critical difference is that they also include this hash of the data that's expected to be stored at that block. This means that Alice has actually given some proof and authorization to store this particular block of data at this particular position. And so later, if Bob is asked to prove that he's actually storing the right thing, this can help him back that up. Now, once the transaction is completed, either normally and Alice tells Bob that she's done with the work she wants him to do, or if Bob decides that Alice is timed out, he can complete the transaction by writing complete the exchange by writing another transaction to the blockchain. Conceptually, this closes the connection, so at this point, Bob cannot be paid for any additional markers with that same transaction ID. It also means that Alice will no longer be able to read data from Bob. Bob has no reason to provide it anymore. When this connection is written, it means that both Alice's reads and writes have been consumed for the work that Bob has done for her, and Bob is paid for the work that he's done in newly created 0Chain tokens. A critical part of this process is that writing this transaction to the blockchain is very much in Bob's interest. This is how he gets paid. Simultaneously, it also commits Bob to storing a certain file contents in the form of a Merkle root. So continuing on our picture here, we left off with a number of reads and writes being performed, and now Bob writes a second transaction to the blockchain. It includes this transaction ID that ties it back to the first transaction that Alice wrote. It includes a marker list, so effectively all those checks that Alice wrote to him get cached in. And we include the Merkle root here, which commits Bob to the file contents that he is supposed to store. So the mining network will then verify this transaction, deduct all the reads and writes from Alice, update the Merkle root, and most importantly, as far as Bob is concerned, create a new token to compensate him. Now, one obvious question that comes up here: what happens if Alice's Merkle root and Bob's Merkle root don't match? Well, we believe Bob. The idea is that if Alice is trying to act maliciously, or maybe she just disconnected, Bob's Merkle root may not necessarily match what she created initially. However, Bob knows that he has these markers, so anytime he's asked to prove that he's storing a certain chunk of data, he has the marker to back up that he's storing the right thing, and he'll be able to connect that via the Merkle path to actually get back to the root of the Merkle root that's stored on the tree. Another issue that comes up in this protocol is we have a good mechanism for paying Bob for all the reads that are being done and for all the writes are being done, but what do we do if Alice uploads a file and then forgets about it? Maybe she just has some data that she wants to archive. So, is Bob forced to store this file forever with no benefit? Well, our mechanism for that is this challenge request protocol. And it's a carrot and stick approach. That is, Bob is forced to prove that he has this file, and if he doesn't, he's punished. But if he does, he is rewarded with new 0Chain tokens. So it's very much in his interest to be challenged and to pass this challenge. Okay, the steps for this protocol and how it work. First, the binding network posts a challenge to the blockchain. And this is done using VRFs so that it's both difficult to predict. There's no chance that any miner will be able to bias the results in favor of his or her friends. And in this process, we assume that the blobber is going to fail the transaction and punish them immediately. Now that seems a little strange, but the benefit for doing it this way is that there's no opportunity for Bob to DDoS the system to prevent being punished. So it's now in his best interest to make sure this protocol completes if he's actually storing the data, and if he's not, well, he's already been punished, so there's no downside. So the blobber provides a block of data that he's expected to provide. It provides the Merkle path in the form of these log end nodes, and there will be a break marker that he's expected to store that translates to this, that matches up with this block of data. All these together give us some probabilistic guarantee that Bob is actually storing the file that he's expected to store. And once he does this, and the mining network verifies that this data is correct, he gets back those tokens that were taken from him in step 1, and additionally gets a bunch more. So this is the carrot and stick approach explained. So I want to spend a few minutes talking about the various attacks that can come up and what defenses we have outlined against them. I'm going to do this a little bit backwards and talk about our defenses first. Now, most central is our economic protocol. Our model is largely built around free, so how exactly do we make that work economically? Well, we have an economics professor from San Jose State who's carefully tuning all these parameters to make sure that any attacks that might come up will not actually be profitable, that everybody following the protocol will be more profitable for them. We also have all these transactions on the blockchain, so that if we identify suspicious behavior, we can potentially take punitive action against those parties. And if for some reason a blobber disappears from our network, if a data center is taken out in a natural disaster, we're using erasure codes so that it's possible for us to reconstruct any missing data. Now, with those defenses in mind, the attacks we have are outsourcing. This is where Bob is expected to store the data, but he's actually getting it from Charlie instead whenever it's needed. Generation, which is in the initial Filecoin paper where the blobber is paying to store data, and then he's just easily able to regenerate that data on the fly without ever actually storing it. We broaden this concept a little bit to also include cases where Bob is trying to store a file and just throw away the file contents, knowing that nobody else is ever going to want to see it. So we also have to consider an additional case where we have these markers, and it's possible that Bob could write a bunch of markers to himself and just churn through and generate a bunch of them. Our defense here is largely based on the economic protocol to make sure that all of these attacks don't actually work out in the attacker's best interest. Now, there's also a type of attack called collusion, where Alice and Bob are both expected to store a certain file, but they can get it from each other whenever they happen to need it. And they could do this off-chain so that there's no record of it. We defend against this by erasure codes so that nobody is actually storing the same copy of the data. And we have Sybil attacks, which are, in some sense, a variant of collusion attacks where there's no friction between interaction with the different parties. Now, a lot of these end up coming back to outsourcing attacks, that if Bob can outsource at least getting some pieces of the data, he could potentially get away without actually storing the resources he's expected to store. So, how do we prevent against that? Well, this could come up when either Bob is expected to provide data through just a normal read operation from Alice, or he's been challenged by the mining network. So the challenge works based on this random roulette wheel style. He is selected to provide a block of data, he's selected to give one specific block, and if he has it, he can easily reply back with the block of data, the marker that matches up with it, and the Merkle path that ties it back to the Merkle tree on the blockchain. If he doesn't have it, his only option is to try to get it from somebody else. He can try to do this off-chain by requesting it from Bob 2, who's also expected to store some of the data that he needs. The problem is that Bob 2 has no incentive to provide this data. He is not authorized by the blockchain, he is not compensated for it, so he'll just ignore the request. Bob can then try to request the data from the blockchain directly. And the problem there is, because we use erasure codes, he'll have to actually get several copies of the data. So doing this, the blobber is going to get paid for providing data once, but he's going to have to pay Bob 2, Bob 3, and Bob 4 in this particular case. So he's paid 3 times and gotten paid once. Now, future work for where we're going with our protocol. We're looking at making our network self-healing. Currently, it's possible that a client can reconstruct data that has gone missing or where there's been a problem. But we'd like to do this automatically so that if we know that there's been any problems where a blobber has failed a challenge, that we can automatically reconstruct that data. We also realized in talking with people about earlier versions of our protocol that is very much block-based storage, that there's actually a lot of interest in providing object storage or file storage instead. So we're looking at developing a 0Chain file system as part of our next version of the protocol. Lastly, our permissioning setup is fairly simplistic at this point. We have public data and private data, and private data is just done solely through Alice encrypting on her end. Proxy re-encryption is an interesting tool where we can actually have more sophisticated variants of permissioning. So we're looking into that as the mechanism for integrating in future versions of our protocol to give ourselves more flexibility there. Okay, back to final thoughts. 0Chain promises to be fast, flexible, and free. The fast part is that we're trying to have very quick transactions with very quick finalization, and as a result, our storage protocol is designed to try to put as little weight on the mining network as possible. We have designed this to be as flexible, in this case meaning that it is modular as possible. So our storage protocol has minimal hooks that it needs into the mining system, into the blockchain. And of course, the free part is that you never lose your tokens in 0Chain if you're a good actor. After you've taken advantage of your resources, use the storage, you can eventually, once they get unlocked, sell them, use them again, whatever it is that you wish to do. Thank you very much for your time.